So this was number 18 from last night's homework, is that right?
Yeah.
Okay. So my goal was to frustrate and annoy you with sine squared x plus cosine squared x, where you try to figure out what to do with those squared trig functions. And my hope was that you would come up with the realization that what does sine squared x plus cosine squared x equal?
I realize now 1.
It equals 1. So this is just the integral from 1 to 5 of 1 dx, or x evaluated from 1 to 5. Yeah, so that was my attempt at fooling you all. Looks like it worked. Congratulations to me. Thanks. That makes sense now, though?
Yeah.
Awesome. Cool. Yeah. Once you actually figure out that that's 1, then it's pretty straightforward, right? But any other ones that anyone had questions on from last night's homework?
Yeah.
Which one? Yeah. Somebody said something.
The paper.
I don't know. I can't hear what you're saying. If you want to type it in the chat, maybe you can do that, but I can't understand what you're saying. Your audio is cutting out. All right. I guess we're good to continue on. So here's what we're going to do. We're going to take a look at some different, two different functions. One that's f of x equals x cubed plus 1, and one where u is equal to x squared. And we're going to see if we can find some antiderivatives and put all of our answers in the end in terms of x. But what we're going to have down here is we're going to have different variables in our f, so f of x and f of u. And sometimes we're going to have dx's and sometimes we're going to have du's. And just kind of try and take a look at how that affects the different integrals. And sort of hopefully solidify in your mind that the variables that we have within our integral need to match up with the dx or the du or the dz or the d theta, whatever d whatever we've got going on. So first off, the integral of f of x dx should be a pretty straightforward one. That's the integral of f of x, x cubed plus 1 dx. And what does that equal? That ought to be
1/4 x to the 4th plus x.
1/4 x to the 4th plus x. You forgot something. Constant. Don't
Plus c.
constant, right? Everybody agree that that's what that one should be?
Yep.
Okay. So now let's take a look at f of u du. So what's f of u in terms of u?
F of u squared.
Not quite, no. So let's look at it this way. What's f of 1? F of 1 is 1 cubed plus 1, right? True. What's f of 10? F of 10 is 10 cubed plus 1. Or what's f of a? F of a is a cubed plus 1. Well, what's f of u? F of u is u cubed plus 1. I don't need to turn that into anything with x's. I don't need to do anything other than just say f of u is u cubed plus 1. And if I put a du there, then I should just be able to integrate u cubed plus 1 du as u to the 4th over 4 plus u plus the constant. But if I want it in terms of x, now I need to replace the u's with x squareds. So what does that give me? X to the 8th over 4 plus x squared plus c. Everybody agree and good with that or no?
Yeah.
Okay. So we'll note that the integral of f of x dx is very different than the integral of f of u du if I have some substitution for what u is equal to in terms of x. Yeah. Now what about this one, f of u dx? Well, what's f of u? We already said f of u is u cubed plus 1, but now we have a dx, and so I can't integrate this as u to the 4th over 4 plus u, because I need to integrate in terms of x, which means that I need to convert this u cubed plus 1 into terms of x before I integrate. Everybody good with that?
Yeah.
So what is u cubed in terms of x? That ought to be x to the
6.
6 plus 1 dx. And what does that give us? That gives us x to the 7th over 7 plus x plus our constant. And so we should note that the variable within our function, within our integrand, and our dx or our du, those variables matter. If I have f of x dx, I get one thing. If I have f of u du, I get something completely different. And if I have f of u dx, then I get something completely different again. Right? So we want to be extra careful that our variables match up with our dx or our du or our d theta. Otherwise, we're going to end up with wrong answers. And the good news is this idea of doing substitutions is going to allow us to integrate a bunch of functions that we might not have been previously able to integrate. Like something like sine x times e to the cosine x. And so what we're going to try to do to integrate this function is we're going to try to make a substitution. We're going to substitute some portion of this out so that we can write it as a simpler function in terms of u that we know how to integrate. But when we write it as a simpler function in terms of u, we have to be able to replace the dx with a du. And so that's going to be sometimes the more difficult thing to do. So I'm going to give us a basic guideline here. And this isn't necessarily something that you're going to follow 100% of the time, but the basic guideline is look at what's the more complicated piece of your integrand. So what's the most complicated piece of sine x times e to the cosine x dx?
E to the cosine x.
E to the cosine x, right? This is more complicated than just sine x, right? That's the more complicated piece. So let's think about this right off the bat. Do I know how to just integrate just e to the cosine x?
No.
No, we don't. But what if we got rid of the cosine and just made it e to the u? If we had e to the u du, could we integrate that?
Yeah.
Yeah, that would just be e to the u. So let's try to substitute out the piece of the more complicated part that makes it hard for us to integrate. So let's let u equal cosine x. That's what we're going to start with. Hold on one second. All right, sorry about that. So we've got u is equal to cosine x. So now what I'm going to do is I'm going to go over here and I'm just going to start rewriting this integral as sine of x, because that hasn't changed. And then I've got e to the u dx. Everyone good or no?
Yeah.
Okay. Now, the problem is in order to integrate an e to the u term, we need to have a du. And we also would need to get rid of this sine x. Well, the good news is if we take the derivative of both sides of this, we'd get du is equal to what? negative sine x dx, right? And this is just like when we were doing differentials, right? We're just taking the derivative of u, that's the derivative of u, and the derivative of cosine is negative sine x dx. Everybody good with that?
Yeah.
Okay. So if we could replace a negative sine x dx with a du, we would then have an e to the u du in here that we could easily integrate. But the problem is we don't have negative sine x dx, do we? We only have a sine x and a dx. So how can we solve that problem? Can I just put a negative sign in here?
No.
No, I can't just put a negative sign in there unless I do what?
Divide or multiply by another negative to kind of
As
cancel
long
it
as
out.
if I multiply or divide by another negative, then that's fine. So let's do that. There's a negative. So could I do that? Negative of negative sine x e to the u dx. I put in two negatives, which should cancel each other out. So I've effectively got the same thing. But now what I've done is I've built in this negative sine x dx into my integrand so that I can replace it with du. So the negative that's outside the integral will stay. And the negative sine x dx will get replaced as a du. And so now I just have the opposite of the integral of e to the u du. And what's the integral of e to the u?
E to the u.
It's just e to the u plus a constant. And so we could just distribute that negative through and say that's negative e to the u minus a constant. Well, minus a constant plus a constant, it's all the same. We're just going to always attach just the plus c to the end. And at some point, it's going to be significant that that if we put the negative sign outside of here, that's a minus when we have to solve for the actual constant, but we're not doing that yet, so we don't really need to worry about that. Everybody good with that so far? That's not our final answer, but everybody good with that so far?
Yeah.
Okay, and why is that not our final answer? What do we need to do?
Make it in terms of x.
Put it back in terms of x. So u is equal to cosine x, so this is negative e to the cosine x plus a constant. And there's our integral of sine x e to the cosine x. It's negative e to the cosine x plus c. You guys see how that worked?
So it's kind of using chain rule to a limited degree along with other stuff.
It is. It's basically the chain rule in reverse. It's a u-substitution, and it works for functions that you would have to integrate using the chain rule. I'm sorry, functions that you have to differentiate using the chain rule. So, if this answer that you get needed the chain rule to differentiate, you generally need a u-substitution in order to integrate that other function. Does that make sense?
Yeah.
All right, let's do another one. We've got the integral of x squared times the square root of 5 plus 2x cubed. So which piece of this is the more complicated part?
Square root of 5 plus 2x cubed.
The square root of the 5 plus 2x cubed, right? So if I could eliminate all of that junk that's inside that square root and just make it a u, right? Root u, we can easily integrate, can't we?
Yeah.
So let's do that. Let's let u equal 5 plus 2x cubed. And so that gives us the integral of x squared root u dx. So two problems. One, x squared is still there and dx needs to be a du. So let's figure out what du is and what is du. U is 5 plus 2x cubed. Du is
6x squared.
6x squared dx, right? And do I have a 6x squared dx over here?
There's an x squared dx.
There's an x squared dx, but not a 6x squared dx. So let's just put a 6 in. Can I put a 6 in? Well, only if I
Cancel it out.
say that again.
Cancel it out.
Yeah, cancel it out, right? With a 1/6. So if I multiply this by 1/6 and I multiply it by 6, I've effectively done nothing to it. But I have built in the 6x squared dx that I need to turn into a du. So we've got 1/6, the integral now of root u du. And what's the integral of root u, or u to the 1/2? That should become 2/3 u to the 3/2 plus our constant. And what does that end up becoming? 1/6 of 2/3 ought to be 1/9. So we've got 1/9 u, which I'll replace with 5 plus 2x cubed to the 3/2 plus a constant. Any questions or issues or concerns about that?
Nope.
All right. Spectacular. Let's do another one. Any thoughts on this one?
U equals 7x.
Okay, so if we try to do u equals 7x, then du is going to be
7dx.
7dx. And I could definitely put a 7 in there and a 1/7 on the outside. But that's just going to give me cotangent u, isn't it? You know what the integral of the cotangent of u is?
Is it on the formula sheet?
Not a thing.
It's not on the formula sheet.
Put it in terms of sine and cosine.
All right, yeah, let's start with that. So we're going to have to do something that's going to be similar to this. So we're going to integrate cosine 7x over sine 7x dx. And now we've got two parts of this. We've got a sine 7x and a cosine 7x. Well, what's more complicated, having stuff in a numerator or having stuff in a denominator? Yeah, having it in the denominator is what causes issues, right? Because if I just had cosine 7x dx, well, that's easy enough to integrate. So I want to get rid of the thing that's in the denominator. So let's let u equal sine 7x. And what does that make du equal to?
Seven cosine of 7x.
Yes, thank you for remembering the chain rule. 7 cosine 7x dx. And so now we'll note that I do have the cosine 7x dx. I just don't have the 7. Well, now I do. And I'll have to throw a 1/7 down in front of it in order to cancel out that 7. And we want to make the point that we cannot make u equal to cosine 7x, because if we try to make u equal to cosine 7x, then the du would be negative 7 sine 7x, but that sine 7x is in the denominator. And so it wouldn't be a sine 7x dx, it'd be a 1 over sine 7x dx, and that wouldn't actually work out to replace your du. Does everybody see that? Yeah, so if you've got a fraction, chances are you're going to want to sub out the denominator and turn the numerator into your du. So we've got 1/7, and now 7 cosine 7x dx is du, and sine 7x is just u. And Alex, I know you know the answer to what is the integral of du over u now because you asked me this last night. What does that become?
I did ask you that last night. I don't think I
Uh,
did.
Well, you asked about x to the negative 1.
Yeah, is that the same thing right there as x to the negative 1?
U to the negative 1.
Natural log x plus c, right?
Yeah, natural log, and I don't think I typed it last night when I was replying to you, but it's actually natural log of the absolute value of, oops, I should write x there. It's natural log absolute value of u plus a constant. And that's on your formula sheet, but you should know what's the derivative of natural log of x? It's 1 over x, right? So the integral of 1 over x ought to be natural log of x. And the only reason we put an absolute value around it is because 1 over x is defined for all real numbers except x equals 0, whereas natural log of x is only defined for positive numbers. So in order to have an antiderivative of this that is defined for all real numbers except for 0, we put an absolute value around it. And so that's why there's an absolute value around it. But make sure you know that one because it shows up a lot. And now we'll replace the u with our u, which is sine 7x, plus our constant. Everybody good there or no?
Yeah.
Cool. So I'm going to sort of deviate away from the notes for just a second. These are two antiderivatives that are not on that sheet. They show up fairly often. You might want to have them memorized. If you don't memorize them, not a big deal, because you can always solve either of them using a u-substitution, but I at least want to show you guys how to do them both. So we just did cotangent 7x, right? So cotangent x should actually be even easier. Oops, I don't know why I started writing cotangent again. Right, this is cosine x over sine x. And if we let u equal sine x, and du then equals cosine x dx, this is the integral of du over u, or natural log absolute value of u, or natural log absolute value of sine x. So you might want to memorize that the integral of cotangent is natural log absolute value sine. And then over here, it's a little bit more complicated because this is sine x over cosine x. And if you let u equal cosine x, then du is negative sine x dx. So you have to put in a couple of negative signs. And you end up with negative natural log absolute value cosine x plus a constant. And sometimes people write this as natural log absolute value secant x plus a constant. So if you want to memorize those, cool. If not, just know how to do those quickly and easily using a u-substitution. Everybody good there?
Yeah.
Yeah.
Cool. All right, let's do some more. Let's look at dx over cosine squared 2x. So what do we think we should do there?
Denominator.
You want to sub out the entire denominator?
How about the cosine 2x, and then you have like u squared or something in the
All right,
denominator?
so if I had cosine of 2x, what's your du going to be?
Would we have to do like another one, like a double chain rule here?
No, we're just going to have to rearrange. This is just not going to work out the way you wanted it to. Right, cosine 2x makes my du negative 2 sine 2x. And to build negative 2 sine 2x into that is a little bit of a problem. The negative 2 is no problem because I can put a negative 1/2 outside. But the sine 2x, I'd have to multiply by 1 over sine 2x, which couldn't go outside. It'd have to be included in here, and I'm just adding in a bunch extra junk. So we're going to have to find some other way to go about this one. That's not going to work out.
Maybe use u squared.
Sorry, say that again.
Make it so we use the chain rule with u squared.
Okay, so what do you want me to do the substitution as then?
Um, I'm not sure.
Okay, anybody else have an idea? We gotta find something to do the substitution with, or we need to rewrite this in a different way.
Oh, secant squared?
All right, let's try that. So let's rewrite this as secant squared 2x dx. Do we know what the integral of secant squared of something is in general?
Yeah.
Yeah.
Okay, so the problem being then we have this 2x. So what do we need to substitute out, you think?
U equals 2x.
Yep, just the u equals 2x, and du will be 2 dx. And so this becomes the integral of secant squared u, and then dx. And we need a 2, which means we need to put a 1/2 out front. Or 1/2 the integral of secant squared u du, which ought to be what? What's the integral of secant squared u?
Tangent u.
Yep. So this just ought to be 1/2 tangent u plus our constant, or 1/2 tangent 2x plus our constant. Any questions or issues with that?
Nope.
All right. Let's take a look at another one. Any thoughts on cotangent squared 3x?
Make it in terms of sine and cosine.
Okay. So let's take a look at that. Cosine squared 3x over sine squared 3x, right? And then what are you going to do?
I don't know, maybe like u equals 3x, probably not going to work, but
Yeah, u equals 3x isn't going to work, because if u is 3x, I'm still going to end up with this cosine squared u over sine squared u, which we still not integrate.
Can we multiply by sine squared 3x and like pull it out of the integral?
And no, you can't pull anything out of there that has an x in it.
Oh, I see. Okay.
Only constants, yeah. So if it was like sine of 3, well, sine of 3 is just a number, so we could pull that out, but not sine of 3x.
Okay.
Isn't cotangent equal to cosecant minus 1?
It is, yes. Let's try that. So we could say that this is equal to the integral of cosecant squared 3x minus 1 dx. Everybody good with that? 1 plus cotangent squared is cosecant squared, so cosecant squared minus 1 is cotangent squared. And let's separate this into two different integrals. Cosecant squared 3x dx minus the integral of 1 dx. Well, this one's pretty easy to do, right? But what do I need to do with this one? I need to let u equal 3x, and du is 3 dx. So we'll put in a 3 and a 1/3 and get 1/3 the integral of cosecant squared u du minus, what's this one? Just x plus some constant. Everybody good with that?
Yeah.
Okay, and what's the integral of cosecant squared?
cotangent.
Almost.
Negative cotangent.
Negative cotangent. So we have negative 1/3 cotangent u plus some constant. Well, if I have plus a constant here and plus a constant here, that's still just a constant being added to it. So we'll just say minus x plus some constant. And if u is 3x, we'll just replace the u with 3x. And we've got negative 1/3 cotangent 3x minus x plus c. Good or no? All right, now we're gonna have to think a little bit. What are we gonna do with cosine cubed x dx?
U cubed.
What's that?
Can we make it U cubed?
No,
U equals cosine x?
we can't. What's the problem with that? U equals cosine x means that du equals negative sine x dx, and I don't have, there's no negative sine x dx in there, is there?
Nope.
No, if I try to put in a negative sine x, I'd have to divide by negative sine x, and then I'm still going to have a negative sine x in a denominator, which is a problem. So that's not going to work. Anybody else see a way to go about that one? Anyone?
So like in the last one, you separated them into two different integrals. Are we allowed to do that with multiplication?
No, you cannot do that with multiplication. You can only do that with addition and subtraction for integrals.
Okay.
But we can still rewrite it within one integral if you want. Is there a way you'd like to rewrite it within one integral?
Yeah, if you do cosine x and then square it, or wait, sorry, if you could we do like cosine squared x times cosine x?
Sure.
And
And
then
why
do
would we
the
want to do that?
substitution,
Wait, say that again, second part again.
and then do the u substitution with the cosine squared x.
Okay, so we've got a good first step here. Let's take a look at this u equals cosine squared x, because that's going to be a problem. If u is cosine squared x, what's du? It's the derivative of this, right? Which is, this is u squared. If we were doing this, is the chain rule derivative, right? So that ought to be 2 cosine x times the derivative of cosine x, which is negative sine x. And so if I sub out the cosine squared x, I don't have a negative 2 cosine x sine x dx. I just have the cosine x. So I'm still going to have to be adding in a lot of extra stuff in there. That's a problem. So I like our first step here, but we still have some more rearranging to do before we can do the u substitution.
Can you change cosine squared x to 1 minus sine squared x?
Okay, so 1 minus sine squared x, that's certainly allowed. I could do that. That's a thing, right? Cosine squared is 1 minus sine squared, just based on the Pythagorean trig identity. Sine squared plus cosine squared is 1. Okay, so then what can I do with that?
Well, then you make u equal to that, because the derivative of sine squared x would give you a cosine, and that's something you have in your equation.
All right, you still got a problem, so we're going to see what's wrong with what you said, but you're almost there. If u is 1 minus sine squared x, well, then du, the derivative of negative sine squared x, is negative 2 sine x cosine x, using the chain rule, and I don't have that, right? I just have cosine x dx, so I'd have to still throw in this negative 2 sine x, which is still a problem. So we're almost there.
You can make negative sine squared x in terms of cosecant.
So you want to make that 1 over cosecant? That's gonna, I think, complicate things even more with getting rid of this cosine.
Could you split the sine squared x into 2 sine x and then make u equal to 1 minus sine x?
I'm not sure what you want me to do. What with the sine squared?
You can separate it into sine x times sine x.
And I could write that 1 minus sine x times sine x.
Could you factor it to be 1 minus sine x plus 1 or 1 minus sine x times 1 plus sine x?
Okay, I could do that. I could do either one of these things. What's the end result that either of you want from one of those? Like, what's the u sub that you would do?
Because if you do, oh, well, then I guess it wouldn't be the chain rule anymore, so you wouldn't get a sine x. Well, you set u equal to 1 minus sine x.
For which one? This top thing or this bottom thing?
The top.
So for the top one, I don't have a 1 minus sine x. I have 1 minus sine x times sine x. You got to remember your ordered operations, right? The multiplication has to come before that. So I don't think this one's going to work out.
Yeah.
So if you guys want to think about this way, if you let u equal 1 minus sine x, then your du is just negative cosine x dx, right? Which we could easily enough build in there. But we're still left with this 1 plus sine x that we have to deal with later on, which is going to be a little bit of an issue. True?
Yeah.
Yeah. It's not as much of an issue as it might be, but there's an easier way to do. This way would work, but there's an even easier way than splitting this thing up further. We don't need to split this thing up at all. We just got to pick the right thing for our u. This is a good idea, but it complicates things a little bit unnecessarily. We should just be able to pick something in here as our u value and then make the substitution. Everything with an x should disappear and we should end up with a function that's easy to integrate. Anybody see what piece of this we can sub out?
Cosine x?
If I try to
Or
sub
do we
out
already?
cosine x, then du is negative sine x dx, which I mean, I got, I have a 1 minus sine squared x, but times a dx, that's not a negative sine x dx, no, not cosine. There's one thing that you guys haven't tried yet.
Do we distribute the cosine x?
Sorry, say that again.
Do we distribute the cosine x?
We could distribute the cosine x. That's going to give us cosine x minus cosine x sine squared x, right? And the cosine x part we could easily integrate, but the cosine x sine squared x, we're going to have a similar problem to where we're sitting right now.
Yeah, I figured.
Yeah.
We set u equal to,
I mean, it'll work. We could do that, but it's like I said, we've got a substitution that we should be able to make just right here. This should simplify everything down really nicely. You guys just got to find it. Luckily, we got another 20-something minutes here and only a few problems to go.
What if you just set u equal to sine squared x?
And I think we tried that. If u is sine squared x, then du is 2 sine x cosine x.
Oh, that's right.
Right, and that's a problem. You guys are thinking too complicated here.
Could you
What
be
is
sine
the-
of x?
Oh, sorry, say that again.
Could you be sine of x?
Oh, I hope so. If u is sine x, what's du? Cosine x dx. So that's nice. And if u is sine x, what do I have left? 1 minus u squared du. Isn't that easy to integrate now?
yeah.
Yeah. So perfect. Just let u equal sine x. What do we end up with? U minus u cubed over 3 plus our constant. And if u is sine x, we'll just replace that in there. Sine x minus sine cubed x over 3 plus our constant. Any issues with that? All right, so make 1 point. Somebody, I don't know who it was because I can't see who's talking when they're talking, said, let's distribute this through, right? If you had distributed this through, we're going to just do this real quick. We had an integral of 1 minus sine squared x times cosine x. If we distribute that through, we got cosine x minus cosine x sine squared x dx. And what's the integral of cosine x?
Negative sine.
Sine x. No, it's positive.
Sine.
Sine x plus a constant. I'm going to ignore the constant for a second because I'm going to have another one in here. So then I would have sine x minus cosine x sine squared x as integral. So I'm not sure who was saying this, but then we would just let u equal sine x and du would be cosine x dx. So if we wanted to do the distributing, we could have done that. And then we'd have sine x minus the integral of u squared du, or sine x minus u cubed over 3 plus our constant, which we would know would be the same, sine x minus sine cubed x over 3 plus our constant. Right, which is exactly what we got doing it this other way, but we didn't have to do an extra distributing and then do 2 separate integrals. And then in a second, we're going to go back to, somebody was saying, I can't remember who it was now, what about turning this into 1 minus sine x and 1 plus sine x? We're going to go back. I think that'll work out, but I want to do a couple more problems and get up to a different point in just a second. So first, let's do a couple more, and then whoever said separating that into 1 minus sine x and 1 plus sine x, I want you to remind me about that in a minute here. So let's take a look at this one. One thing that's a little different here is we've now got a definite integral, right? Just going to complicate things a bit. Anybody see a u-substitution or just know how to integrate this?
What if we did u equals tangent x?
Sure. If u equals tangent x, then what's du equal?
It's secant square, yeah.
It's weird. So we've now got an integral of u du. Now, we have a problem though, which is, what was this function in terms of? Our integrand was all in terms of
X.
x. And what does that tell you about these values? Those values are x values, aren't they?
Yeah.
So now I've got an integral in terms of u. I don't want to have x values that I'm evaluating this at. I want to have values of u, right? So I need to figure out what is u equal when x is 0. Well, what's u equal when x is 0? Tangent of 0 is
0.
0. Okay, so that's fine. What about, what does u equal when x is pi over 3? What's the tangent to pi over 3? That should be like all 29 of you at once unmuting yourself and telling me that the tangent to pi over 3 is √3. You should all know that value. So our upper limit is now going to turn into a √3. And these are now u values. And what does the integral become? U squared over 2. And I no longer, when this is a definite integral, need to convert back into terms of x, because I've changed my x values into u values, so I can just evaluate this at u equals √3 and u equals 0. So we got √3 squared over 2 minus 0 squared over 2 which gives me 3/2. So actually having a definite integral, it adds in a little bit here, but you don't have to convert back in terms of x at the end. You can just evaluate it in terms of u. Now, if you wanted to convert back into terms of x and say that the integral of this was tangent squared x over 2, then you'd have to go back and evaluate that from 0 to pi over 3. You have to go back to your x values, but there's no reason to do that. It's just extra work, more chances to make a mistake. My suggestion is it's a definite integral and you do a u substitution, convert those limits, and then just evaluate. Everybody good there?
In the beginning, when you did the substitution, where did the secant squared go? Because like you just rewrote it as integral of u du.
Right, so somebody told me let's let u equal tangent x, which makes du secant squared x dx, right? The derivative of tangent is secant squared x.
Mhm.
And so the secant squared x dx right here turns into the du.
Oh, okay, thank you.
Yep. Did anybody else see another substitution we might have done with this? Just out of curiosity. I'm gonna go through this real quick. We had secant squared times tangent, right?
Yeah.
Well, you might have also noted that that's the same as secant x times secant x tangent x dx. And you could have let u equal secant x, and then du would have been secant x tangent x dx. And so we could have also said this was the integral of u du that way, with u equal to secant. And then we would have had to go in and say, well, what's the secant of 0? What's the secant of 0? You should all have been muting yourself and saying that the secant of 0 is 1. And what's the secant of pi over 3?
2.
2. So we should have then said that this was equal to the integral of u from 1 to 2, which would have been u squared over 2 from 1 to 2, which would have been what? 2 squared is 4 over 2, which is 2, minus 1/2, which is 3/2. So I'm going to come out exactly the same. And then one other thing that we might want to note here is that either way we did this, we ended up with u squared over 2, right? Suppose this was not an definite integral. Suppose it didn't have the limits on it. Suppose it was an indefinite integral. Could we have still done this substitution either way, with u equal to tangent or u equal to secant?
Yeah.
Yeah, we should be able to, right? So let's take a look at that. The integral of secant x tangent squared x dx. We could have said u equals secant x, or we could have said u equals tangent x. And either way, we would have ended up with u squared over 2 plus a constant. True?
Yeah.
Yeah. Which in this case was secant squared x over 2 plus a constant, and in this case was tangent squared x over 2 plus a constant. And those are clearly, I mean, secant squared x over 2 and tangent squared x over 2 are clearly two different things, aren't they? So how could both of these be correct answers?
Because they're for different values of u.
But they should, since we converted back to x, these should be equivalent to each other, shouldn't they? I mean, the integral of this function should just be the same function, shouldn't it? Seems like it should be. So let's see if we can figure out why we got two different values. Secant squared x over 2 plus a constant, and tangent squared x over 2 plus a constant. Is there a way to rewrite tangent squared x? Oh, sorry, to rewrite, well, let's do this the other way. Is there a way to rewrite secant squared x? Let's do this way, so I have more room over here. Secant squared x is the same as what?
1 over cosine squared.
1 over cosine squared. What else is it the same as? 1 plus tangent squared x over 2 plus a constant. And so what do we end up with here? Well, this ends up being 1/2 plus tangent squared x over 2 plus a constant. Well, if we call this constant 1, and we call this constant 2, right? They don't have to be the same constant, right? We said these could be any constants. So what does that tell us? It tells us that tangent squared x over 2 plus 1/2 plus constant 1 is the same as this up here, which means that constant 2 is equal to constant 1 plus 1/2. So the constants that we get in each case are different from each other, but each of these things still have the same derivative. They both still have a derivative that is equal to tangent x secant squared x. Even though they look very different, they and are not equal to each other. They're definitely not equal to each other. They only differ by the constant, because I can turn this one into the same thing with a different constant. So that's the reason why we could have done either u-substitution. Everybody see that sort of? Any questions or issues there? Yeah. Okay, everybody good? Cool. All right. Let's do another one of these with a u-substitution and a definite integral.
The denominator, go u equals x squared minus 4.
Okay, u equals x squared minus 4. What does that mean du is equal to?
Two x.
2x dx. And so we'll need to put in a 2 up here and a 1/2 on the outside. So we got 1/2 the integral of, in the numerator, I have 2x dx, which is du. And the denominator, I have u. And what's the integral of du over u? Alex, I know you know this one. It's 1/2.
Natural log, or like absolute, or like natural log absolute value of u plus a constant.
1/2 natural log absolute value of u plus our constant, which gives us 1/2. Oh, sorry, I don't know why we put the constant on there. I already had written it when you said it, but we need to evaluate this. But can we evaluate from 0 to 1?
No, those are
No.
x values.
Those are x values, so we need to convert them to u values. So 0 squared minus 4 gives us -4. And 1 squared minus 4 gives us -3. So we've got 1/2 natural log of the absolute value of -3, which is just 3, minus the natural log of the absolute value of -4, which is 4. And that's a good answer. But if this was the AP test and this was a multiple choice test, they might have it written in a bunch of different ways, right? You could rewrite natural log of 3 minus natural log of 4 is natural log of 3/4. So you might see an answer that looked like that, or a constant out in front of a logarithm could be applied as an exponent. So you might see this as natural log of the square root of 3/4. Or you might see it as natural log of √3 over 2. You could see that as any of those different forms as a multiple choice answer. If it was my quiz or if it was a free response question on the AP test, any of those would be perfectly acceptable, but just know how to convert between them in order to get a right answer on the multiple choice part. Everybody good there so far? All right, let's do one more of these. And then I want to go back to that 1 plus sine x, 1 minus cosine x idea that we had the other, I don't know, 5 problems ago or so. So what do we think? What should u equal for the integral of 4x over root x squared plus 9?
X squared plus 9.
Okay, so u equals x squared plus 9. Du is 2x dx. Do I have a 2x dx up there already? Yeah, I've got 4, right? So I could take a 2 out of it and leave a 2x up there. Everybody good with that? Just pull part of the constant out, and then the other constant will stay there and get replaced with a du. So this is a u to the negative 1/2. So if I integrate u to the negative 1/2, what do I end up with? A u
1/2 of the square root of u.
Yeah,
U over 2.
we end up not u over 2. Let's write this out just to make sure we don't make a little mistake. This is the integral of negative 1/2 du. So that becomes 2 u to the 1/2, right? Because we have the 2 out in front, divided by 1/2. If you divide by 1/2, what are you multiplying by? By another 2. So this ought to become 4 root u plus our constant, which is 4 root x squared plus 9 plus our constant. Good or no?
Good.
All right, cool. Let's see. Yeah, that's where I want to sort of stop. So I want to think back to that problem we had a long time ago, right? We had the integral of cosine, was it cosine cubed, right?
Yeah.
Which we turned into the integral of cosine squared times cosine, which we turned into an integral of 1 minus sine squared times cosine, which then somebody said, let's turn this into 1 plus sine x times 1 minus sine x times cosine x dx. And then they said, let's let u equal, and I can't remember, did they say let u equal 1 plus sine or let u equal 1 minus sine? It doesn't really matter, but let's just pick the first one. Let's let u equal 1 plus sine x. What does that let du equal?
Cosine x.
Cosine x dx, right? So the cosine x dx is there, and the 1 plus sine x, which is our u, is there. So this becomes an integral of u times 1 minus sine x times du. And so obviously we still have a problem here. We still have a 1 minus sine x in there. But there should be a way around that. Anybody see a good way around that?
Distribute the u.
One thing we could try is we could distribute the u to make it u minus u sine x.
And then substitute it in.
Yeah, so we don't actually have to distribute it before we can substitute things in. The only thing that's causing a problem in here is this minus sine x, right? The 1's not causing a problem. only the minus sine x's. So over here, I could determine that negative sine x is equal to, or even we could just say that sine x, let's just do that, that sine x is equal to u minus 1, right? You all agree that sine x is equal to u minus 1?
Yeah.
Yeah.
And so then this ought to become an integral of u times 1 minus u minus 1 du. And now that's all in terms of u. So we've got an integral of u times 1 minus u minus negative 1, which ought to be 2 minus u du, which would give us, I'm going to go to a new page for this, which would give us what? An integral of 2u minus u squared du. Everybody good with that?
Yep.
Mhm.
And when we integrate that, what do we end up with? Should get u squared minus u cubed over 3 plus our constant. And what was our u? Our u value was 1 plus sine x, right? So this ought to be 1 plus sine x squared minus 1 plus sine x cubed over 3 plus a constant, which looks different than what we previously had, doesn't it?
Yeah.
Yeah. But it is either equivalent to or it just differs by a constant from the value that we got of, I think it was sine x minus sine cubed x over 3, I believe is what we had. So we could go through and see if we could simplify this out. I don't know. I've not actually done it this way in advance because I wasn't planning on doing this. So let's real quickly see if we can get this to look pretty equivalent. So 1 plus sine x cubed ought to be 1 plus 3 sine x plus 3 sine squared x plus sine cubed x. And then this whole thing is over 3. Yeah, it's not going to come out real nicely, I don't think, to look at this. Well, maybe it will. Yeah, I think it actually is. So we end up with 1 minus 1/3. And then we have a 2 sine x. And then this is a minus sine x. So that's plus sine x. And then we have a sine squared x minus sine squared x, which will cancel, and a minus sine cubed x over 3 plus a constant, which gives us 2/3 plus sine x minus sine cubed x over 3 plus a constant. And we'll notice that this piece of it, sine x minus sine cubed x over 3, is exactly the same as what we've gotten before, plus a constant. And the only other thing we have attached to it is another constant. So our result that we got just differs by a constant from our original answer. And both are acceptable integrals for that. Everybody good with that or no?
Yeah.
Cool. So we'll stop there. Deshaun, I saw your question, so just hang around for a second afterwards and I'll explain that to you once I let everybody else go. I just got 1 or 2 other things to say. So first off, I'm going to post a homework assignment that you won't be able to complete yet. It'll be due tomorrow. It's got 40 integrals. I will specifically say in the Google Classroom post exactly which ones you are able to do so far. We're going to cover just a little bit more of these u-substitution integrals tomorrow and do some stuff with what's called initial value problems. That'll be the end of this quarter's new stuff. We won't really do much new on Friday. We'll have a quiz on Friday, which I will spend a lot more time tomorrow talking about. What we do tomorrow won't take very long, so I'll have plenty of time to review any questions that anybody might have. Don't forget to donate to the Covers for Lies Drive. I saw a couple people sent me messages during class. I'll respond and add that into my spreadsheet of the total sometime in the near future, sometime today. So when you get a response from me, you'll know that it's recorded. Other than that, have a wonderful day. See you all tomorrow. And if you have questions, hang around and I will answer them.
Thank you.